screen, and then we're going to do the slide deck from beginning. And then I'll display settings, swap the screen. Hi everyone. My name is Rob Canzaneri, and I'm the chapter leader of the data architecture group. I have a little bit of an echo here. I'm going to try and figure out what's going on. Let's see. Maybe that's better. Okay, it seems like it's better. And I'd like today to welcome Brian Mitchell. He's going to give a great presentation on SQL 2014 and updatable column stores. Before we start, I have just 2 or 3 slides to go through. PASS Summit is coming up, and I have a code. It's called VCSUM07, and I've been told that this will save you $150. So that's kind of neat. So use that code if you're registering for Summit, and it'll save you a little money, a lot of money actually. So PASS has been around for quite a while now, and they have a lot of virtual chapters. And here's a list of the virtual chapters. So if y'all are interested, go to PASS website, and you can sign up for any of these virtual chapters. And they always have virtual meetings online. And you know, it's just really neat to take a lunch and learn some new stuff, and you know, it's just a great organization. And my last screen is, you know, PASS is always looking for volunteers. So if if you can have some spare time and you want to volunteer, log on their website, and they always have opportunities and to get involved, and you get to learn and network and get deeper with SQL Server. Okay, with that, I'm going to turn the presentation over to Brian, and let's see. Brian, can you hear me?
I can hear you.
Great. So so see if it comes up.
Yep, switching on my screen now. Well, that's coming up. I'd reiterate what Rob was saying about PASS and getting involved. It's just getting involved in PASS, whether or not you're volunteering at a local SQL Saturday or presenting at your local users group. Is a great way to get involved in the community and to meet new people. It is so much easier to meet new people when you're involved in a community than it is when you are just passively showing up at presentations or SQL Saturdays or what have you. But I would definitely start with your local users groups and your communities, or even the virtual chapters like this. Anything you can do to be involved will always make it so that your network grows much, much faster and much deeper, to be honest. So I'm assuming you can see my screen at this point. And
Yeah.
I'm going to go ahead and...
Yeah, Brian, I can see it.
Okay.
I wanted to add one thing. I'm sorry to interrupt you. That this session is recorded, and we're going to put it on YouTube. And there's going to be a link from the main PASS website, so you can link over and see this session later on. And if you have any questions, please just email myself or Brian, and I'll make sure he gets the emails, and we'll get you an answer to your questions. We're kind of limited on time. We got an hour, so in less than an hour, we're going to shut it down. But I want to thank everyone for coming again, and Brian, it's all yours.
Very cool. So this is a presentation I've done a few times around clustered updatable column store indexes that were introduced in SQL Server 2014. As he said, my name is Brian Mitchell. I'm a lead architect in Microsoft's Big Data COE, so it's within Microsoft services. So I am out in the field, going to customers, sitting down, and trying to implement a lot of these solutions, usually around, lately for me, around HDInsight and PDW, more so than standard SQL Server. But I got introduced to the clustered updatable column stores through PDW, who's had it in the product for about 1.5 years longer than SQL Server Standard has, or SQL Server Enterprise has. So been living it a little bit, and it's a great topic, especially for you, those of you that are really interested in the data warehousing space. And hopefully you'll find what we're going to talk about pretty interesting here. So I'm going to, so really, you know, at the end of the day, what we're talking about is, as our data sizes grow, we need to be able to handle those things through, you know, efficient storage subsystems with interactive query responses. As our data sizes have grown, traditional methods using standard SQL Server indexes and standard, you know, row-based storage has made it more difficult for us to have those interactive query response times, and really be able to handle the kind of system size and system speed that we want for our traditional data warehousing. Clustered updatable column stores or cluster column stores, advanced SQL Server for these challenges, and it's a really exciting space for those of us at Microsoft to really kind of introduce to people, because it is a place where actually Microsoft is being a leader in the industry when it comes to a standard relational database management system, having native column stores built right into the product that really handle these challenges in a very efficient way. And of course, these capabilities need to be handled in a really simplistic management space. So, having Management Studio handle all of this for you is really important for us. So the agenda, we're going to talk a little bit about the motivations and design principles. We'll talk about how column stores and batch mode speed up queries. We'll talk a little bit more about loading clustered up column stores, which is a pretty important topic. And then we'll finally wrap up with optimizing and database and index design, which may be of more interest to some of the people on this call, which is really kind of digging deep into, okay, now that we're using these, what are some of the things I need to look at to make them efficient? And then finally, we'll finish up with optimizing queries. So the design principles are basically that we are really kind of working around a data warehouse. The idea is that, generally speaking, in a data warehouse, to use column stores, we want to use data that has basically been written once, read many times. That doesn't mean we can't update it, but the design principles should, generally speaking, be for those kind of tables where we are writing data once and reading many times. It's not Hadoop, where it's not that we can't update, it's just that it is much more expensive to update column stores than it is row stores. And we'll talk about what that means. So think of column stores being very efficient for data warehousing environments, more so than OLTP environments. Also, really start thinking about that this is really for queries against large amounts of data. Think hundreds of gigabytes and terabytes of data is really where you're going to find a lot more of your efficiency. That being said, the demos I'm going to show you are on literally hundreds of megabytes of data, and you'll see significant improvements there even. But really, generally speaking, for enterprise sizes, we're talking about large amounts of data. And we're talking about places where we're really dealing with star and snowflake schemas, where they tend to be common, because we're thinking of fact tables and dimensions, Kimball-style data warehousing design, where our fact tables are in the middle, our dimensions are on the outside, and generally speaking, we're targeting our fact tables, because this is the place where we tend to write once and read many times. We don't tend to update our fact tables a lot, as opposed to our dimensions can be updated quite a bit. And so think of the targets for your column store indexes to be at the fact table level within your Kimball-style data warehouse. And then, another design principle is we typically want to append data to fact tables. In other words, we want that data to come at the end of it, so it's probably going to be ordered by date, so that as we're loading new data by date, or just a random, not a random key, but a incrementing key, so that we can just append data at the end. And actually, from a design principle standpoint, what we're really thinking about is actually doing partition switching in on a regular basis. And of course, I've already talked about how we generally think of fact tables being, updates to those fact tables being relatively rare. So before I dive in too far, let's take a look at what I'm talking about a little bit. So I'm going to share my screen. Basically what I have here is I have a virtual machine that is set up for SQL 2014. And in here in SQL 2014, I have a couple databases. One's a database with a cluster column store index, and then another one's with a non-cluster column store index. And I'm not even going to show you what the queries for some of these things look like without the column stores, because they take too long, like literally a minute or two to run, and it's really just kind of pointless. But basically, I have a website here or a reporting services webpage that looks at some of that data sitting in those tables and wants to bring it up. And if I run this particular report against a standard SQL Server table with the proper indexes on it, it takes about a minute and a half for this web page to come up. On the other hand, if I run it against a non-clustered column store index from SQL 2012, that was first in SQL 2012, I can go ahead and design it. I can go ahead and run it, and non-clustered, and I view the report. This will come up in about a second or two, which is pretty good. That's actually pretty smooth. On the other hand, the problem with the non-clustered column store indexes that were introduced in 2012, they're also available in 2014, is that they are not updatable. They are non-updatable, non-clustered column stores. So if I had these non-clustered column store indexes on these tables and I wanted to insert new data, that would make it somewhat problematic for me because I would have a problem. On the other hand, if I go change my, apologies, source properties, if I change this to clustered column store table database and go ahead and run this same report and view the report, you'll see it also comes up in just a second or so, which is pretty good. It's a little slower than I would expect, to be honest. There we go. So it came up, and so you can see there's 101 million rows in there. And so it's relatively, compared to the non-clustered, if I run this a second time, you'll see it came up really fast. Compared to the non-clustered, it's really, there's not a win there. The difference is, for this particular table, set of data, I can go ahead and go into, that database, and I can go ahead and start running some queries that actually go ahead and insert data into that table. And it's just going to loop through and continue inserting data into that table. And if I go back to that, report and now do a view report, it's not adding data. I've done this demo a dozen times and never had a problem with it. Of course, when it's getting reported for YouTube, I do. It's inserting data. I wonder if I'm blocked on something. I bet I am. All right, I'm going to come back to this. I have a feeling I'm blocked on. This was hanging out here, and for some reason I have a feeling I'm blocked on it. I apologize for that. I'm going to go ahead and close Management Studio. I'll come back to this if we have time towards the end. I think I had an open transaction there that was blocking us, and I apologize for that. I'll come back to it if we have time at the end after we've talked about everything. Current. All right, so we'll come back to that. Again, apologize. So let's go through and let's talk about how Columnstore speed up queries, the architecture and the process. So talk about traditional storage models. So traditionally, we store data in row store, on pages, in heaps, with B trees, in SQL Server. And you can also do key value pairs outside of SQL Server, but it tends to be very relational, dimensional data. But we're storing data row-wise traditionally. And so what that means is that it's been relatively inefficient from a perspective of a typical data warehouse. So think of a fact table in a data warehouse. Oftentimes you are dealing with tables that are very wide in nature. And for example, I was at a customer last week where we were literally looking at a 600-column wide table. And in no circumstances would they ever query all 600 columns at any given time. In fact, they probably only query 10 or 12 of those columns in any particular query. But when you have a 600-column wide table and you place that onto a page in SQL Server, that fills up a page very quickly so that you're not storing very many rows into any particular page. And when that happens, whenever you do any queries of that table, you're doing a significant amount of I/O to pull that data off of disk and pull it into memory so that you can query it. And whenever you have that much I/O and you're really only dealing with maybe possibly 1 or 2 rows per page, it really significantly degrades your experience and degrades the ability to really kind of access that data as you're scanning across the entire corpus of the data looking for your answer in a typical data warehouse scan query. So what you need to be able to do is, if you're only querying 10 of those 600 columns, or let's say 10 out of a more typical 80 columns, you want to be able to just access those 10 columns. Instead, when you're dealing with a row store, you're dealing with all those columns every time because you're pulling it up one row at a time. What a column storage model does is it turns everything on its head. And that is, it turns it into a column store where each page stores data from a single column now. And what that allows us to do is multiple things. First of all, each page is storing a single column for that table, and it's able to store just the data for that column on that page. So if we're querying 10 columns out of a total of 80, we only have to query the pages that have those columns. So we've eliminated the other 70 columns from even coming up into memory. We've just left them on disk because we don't need them, which significantly improves the query performance time. Second of all, because we're storing data by column now, we get a lot of rows onto each page because we're only storing hundreds, however many you can into that particular page, but most likely hundreds of rows for that column in there, which allows us to highly compress the data, which means more data fits into the page, which means more data fits in the memory, which means you have less I/O, which means you improve performance. And we'll talk a little bit more about what that highly compressed looks like, but that's a really important aspect of what the Columnstore storage model in SQL Server does. And then, like I said, each column can be accessed independently. You only fetch the columns you needed, which again dramatically decreases I/O. So we decreased I/O by eliminating columns, and then we decrease I/O by significantly compressing the data that we have in any particular column as we, on any particular page for that column. So that structure looks a little bit like this. We have things we call segments, and we have other things we call row groups. A segment contains the values for one column for a set of rows. So the segments are those vertical things you see. The segments for the same set of rows comprise a row group. So virtually, for a set of about 10,000 rows, they're all compressed into a row group that goes onto a segment, and we compress those. So we compress those segments, and each one of those is separate, stored in a separate blob, and that segment now becomes the unit of transfer between disk and memory, and we move that up and forth. So you'll hear us talk a lot about segments, and you'll hear me talk lots about row groups as we go through some of these slides. They're very important terms. So let's look at what an example might look like. If you take a standard SQL Server table that we might have, and this looks fairly familiar as a fact table from anybody's fact table that we have. And let's talk about how you process this column store. So let's take this table, and the first thing that SQL Server does is it horizontally partitions everything into row groups. So approximating out to about 1 million rows per row group on the first pass. So each row group gets about 1 million rows. And then the next thing that we do is we go off and we vertically partition each one of those row groups into segments. So you partition those off into segments now. And once we've done that, then we compress each segment. And this is the important part. So we take those segments and we compress them. And we eliminate all the duplicates. And you'll see that some compress better than others as you start compressing them. But the idea is we get rid of all the extra data. Next thing we do is we do segment elimination for queries. So once we queried something, for example, you see the query up there where we're querying product key and sales amount where order date key is less than a certain date, we can eliminate all those other columns and not even have to pull them off a disk to answer this query, which is very different than the way SQL Server traditionally has dealt with data in the past by storing data in row groups. You had to bring up the entire row, even though you're only dealing with a few of the columns. So in this case, we only bring up some of the columns, and we've eliminated half the data right off the bat. And then with the order date key, you can see there that we can eliminate other segments or other row groups also. So we've eliminated segments, then we can eliminate row groups, And it can be very efficient about eliminating row groups because there's a header at the top of each row group that says, I have data stored in here from X to Y. So, for example, if we're looking for where order date key is less than 2010-1108, it can look in the header of the second order date key and see that, hey, none of the data in here belongs to that group, so I can completely eliminate this row group and not even have to bring it up. And so that allows us to answer the query much more efficiently. So that's one thing that we've done. And if you think about this, that's really improving I/O, which is really important aspect of improving the performance of a typical data warehouse. But I/O is one of what I would call 3 canaries in the coal mine when it comes to performance. And so you design to eliminate I/O, and then the other 2 canaries in the coal mine are CPU and memory, right? So the first thing we've done is we've actually drastically reduced the amount of I/O per disk. We've actually dramatically reduced the amount of memory that we have because we're compressing in the column stores much more efficiently than we would have in a traditional row group. And then the third thing we can do is we can significantly improve CPU utilization by processing in batch mode. And batch mode was first introduced into SQL 2012, and it was significantly improved in SQL 2014 to really improve the performance of queries as they run through the query processor. And what it does for you, in essence, is it moves data in batch through the query plane operators, so it minimizes instructions per row. And what we mean by that is that basically we're getting very deep into the weeds here, but the on-disk cache is being used much more efficiently by processing in batch mode. In other words, we've efficiently made it so that the batch sizes that come through the on-disk cache of the typical servers that are running these queries is just enough to fit in there so that you can process all of it in one group as you move that batch in and out. So we can eliminate doing row-by-row processing, and we can do processing and do effective math across a group of 10,000 rows at a time, which makes it much more efficient, means a lot less CPU utilization, and it significantly improves your parallelism. So the query processor basically moves about 1,000 rows at a time. I keep throwing 10,000 in there. I did it earlier, and I just did it again there. I'm sorry, that's from a completely different topic that I was talking about this morning with a different group, so I apologize with that. But here you're processing about 1,000 rows at a time through the batch processing, and it's able to efficiently do the math that it needs to do on those 1,000 rows, all at the same time as it moves it through. Now, like I said, it's optimized to fit in the cache, and it can do things like filter and hash join and hash aggregation all in batch mode. And what that means is we don't have to loop through every row to do that, or we can just do it for all 1,000. And it can significantly reduce the amount of CPU time, 7 to 40x, which really improves the performance of the CPU. This only can be done when you're storing data in Columnstore indexes. So I'm going to start talking a little bit about what we're doing with the cluster Columnstore indexes to make it an improvement over what we had in SQL 2012 with the non-cluster Columnstore indexes. All right, so in 2014, cluster column stores are also updatable. That means that, let's start with the beginning. You still get the fast execution of data warehouse queries because we're storing it in Columnstore. It's really important to understand that when you make your table clustered, column stored, is that you don't have a separate base table anymore. So if you think of your traditional SQL Server table that you have, and it starts off as a heap of data, then you add your first clustered index to it. That reorders your data. Now you have a clustered index of data. And then you add non-clustered indexes on top of that, and that basically takes a copy of those columns that you choose for your non-clustered index and puts it somewhere else on disk and stores that. So now you have a copy of that column sitting on top somewhere else that's specifically organized for that particular index on top of your base table with your clustered index. And then you make other indexes, and in a typical data warehouse, you often do that dozens of times. You might do it 5, 10, 20, 30 times where you have 30 non-clustered indexes across a fairly wide base table. So now you have multiple copies of multiple rows sitting everywhere. So it really expands out the amount of space that you are storing for that amount of data. With a clustered column store index, you no longer have a separate base table. You no longer have separate non-clustered indexes. It literally takes that first table that you had that eat the data, it then breaks it up into those million rows, those million row chunks that we talked about for your row groups, and then does the processing, the segmentation, and the compression, and stores that data. And it's stored in clustered column store format. And that's really important to understand is it is a native column store format save. So once you've done that, that saves a lot of space because there's now no need or no ability to create non-clustered indexes off of that because you don't need it. Also, with the clustered updatable column stores, we can now insert, update, and delete data for simpler management. It's still, the basic tenet is it's still data that you really want to write once and read many times as much as possible, but when you do need to update it, and I'll explain how those updates occur, we can do that so that you can handle those updates and you don't have to drop indexes to be able to do that. And so that, like I said, it eliminates the need for other indexes, which saves space and simplifies management. And we have lots more data type support in 2014, and I'll get to some of those. So let's look at some of that space savings. And I'm just going to do a typical example using fax sales within AdventureWorks and what that might look like typically if you blew it up a little bit. So you take that table and you start adding some customary indexing to it. So you take it and you start looking at some of the columns that people might be querying by. You start adding some non-clustered indexes. And that table could probably look something around 19.7 gigabytes. In fact, this is a real-world example of some space saving that I was trying. So think of 19.7 gigabytes a day you're moving in now. Now let's think about it. Let's take that same table and let's apply page compression to it. That really significantly decreases the amount of space it uses, practically cuts it in half. So page compression alone, which was introduced, what was that, 2005, 2008, is really good, helps you save a lot of space, which is good, but we could probably do better. Let's take all those indexes off. Let's go back to a table with no indexing. You can see that that original base table was at 5 gigs, so that's pretty normal. I take a 5 gigabyte table, I add a bunch of indexes, next thing I know, it's a 20 gigabyte table, and that's pretty typical in a data warehouse. Now if I want to apply page compression to that table, I only get it down to about 4 gigs, which is good, but I have no indexes on it. So it's just a heap, I have no indexes, performance is going to be horrible, pretty much no matter what I query across it, so that's probably not ideal either. Now, let's take that table and add column store indexing from SQL 2012 or non-clustered column store indexing in 2014. So you're taking that base table and you're adding non-clustered column store indexes across all the columns in it. That's only 6.9. That's a lot less than the 10.9 with the table with customary indexing. It's probably going to perform really well, but what you have there is you have the base table and then you have the non-clustered column store indexes, and they're not updatable. Sitting there, over there, and that takes about 6.9 gigabytes space. On the other hand, with 2014, you take that base table of 5 gigabytes and you apply clustered column store indexing to it, and you end up with a table that is 1.8 gigabytes in size. You can update it, you can insert into it, you can delete from it. It doesn't require any additional indexes. It does everything you need to do, and it takes up, well, it takes up about 90% less space than the table with the customary indexing that might have performed decently, but it's going to perform better than that table with all that indexing in most circumstances with most queries. So you can see the benefits right off the bat there in that we've really significantly reduced the amount of I/O that you're going to have to do to really query across that data to get efficient querying. And that's the key. And in fact, when you start getting down to data sizes like that, that means it's more likely that data is going to be sitting in memory, which means it's more likely that it's in cache, which means it's more likely that you don't have to go to disk in the first place to get it, which means it's more likely that it's going to satisfy your queries very efficiently, and it's just going to make your system run a lot better. The structure of that column store index kind of looks like this. How do I describe this table? So a few things you need to see. Over to the right, you can see that basically we have a few different things that are part of a partition for a column store index. You have your column store space, you have a delta store, and you have your deleted bitmap. And we'll talk about each one of these. So let's talk about when you use the statement create clustered column store. What that does is it goes ahead and it organizes and compresses the data into the column store format. So it'll take all your data from your base table, it'll pick it up, it will break it off into segments, or first of all break it off into row groups, then break it off into segments, and then compress it and store in the column store. And now that your data is sitting in the column store, then some of the other things that you can do is you can, for example, do a bulk insert. If you do a bulk insert into data, what that's going to do is that's going to create a brand new column store row group, and basically and it'll compress it and break it up into segments and then compress it and insert that as a new row group into your column store. On the other hand, if you do some simple inserts into that data, the rows are first placed into the row store, which is also known as the delta store down there at the bottom. It uses two different names, and you'll see people use both of them. So it's kind of good to see them both on one slide so that it confuses you now, so you can get that over with. That delta store down at the bottom, that's just a heap of data. So it's just like a normal table without any indexes. It's internal to this table, but it's basically just a heap so that we can insert the data very quickly and not have to worry about compression or everything like that. When this new column store, when this delta store or this row store gets filled, in other words, when it gets up to about 1 million rows, we go ahead and create a new clustered column store row group, break it up into segments, compress it, and then push it into the column store, and then the delta store is sitting there empty, ready for the next set of data to come in. If you want to delete data, we use the old journaling technique. We have that data sitting out in the column store. That data is sitting there across multiple segments. It's in a compressed format. It's not easily accessible from an insert or delete standpoint. Or an update or delete standpoint. So what we do is we just mark it for deletion for the next, and basically that's what that deleted bitmap is over there. It basically says I want to delete this row. As we query data, we always look at the deleted bitmap to see what rows we need to eliminate, and it will stay that way until the next time that you rebuild your index. When we rebuild the index, we'll go ahead and delete out all the rows that were sitting in there that were marked for deletion. On the other hand, if you want to do an update of a particular row, we do an old journaling technique where we delete the row and then we add it as an insert back down in the delta store. So we pick up that data, we delete it, we mark it for deletion, and then we insert it into the delta store. Once that delta store gets full with about 1 million rows, it gets pushed up into the column store, and we'll go forth. And then we'll go ahead and delete all that data later on when we go ahead and rebuild our index. Building this out a little bit. So we have, to the end user doesn't see any of this. To the end user, this is just a table that I'm querying data, I'm inserting data, I'm deleting and updating data. I don't have to worry about how that's being managed on the back end. It's all just being managed by SQL Server for me. But it's really kind of good to understand the structure of it so you don't go applying clustered column store indexes to every table you have out there, including OLTP, because you can imagine that this would not be a great scenario for an OLTP solution because we're not really deleting data. Now we have copies of data everywhere. This is really a great place that we really want to use for fact tables within data warehouses that we do not update very often. So in 2014, we now have more data type support. So in 2012, you can see the data types we supported. In 2014, we improved our support except for a few things like CLR types and in-var car max and var binary max, XML and spatial. There's ways to get around these things, and I'll talk about them in a little bit. But really, from a fact table perspective, this makes a little sense. Generally, you're not seeing these types of data types within your fact tables. And I know for every 9 people that are shaking their head, yes, there's somebody on the call that's going, yeah, but what about my one case? And we get it. We have some workarounds for that, and I'm sure that the product group is probably looking at including these in future releases. But the data type support that they have at this point covers most of your scenarios you're going to have for a typical fact table. Moving over a little bit to batch mode processing. So I talked a little bit about batch mode processing before. In 2012, there were some limitations that caused queries to run in row mode instead of batch mode. Some of those have been updated or improved in 2014. And basically, if you want to know whether or not you're running in batch mode or row mode, you can go over to the execution plan and take a look internal, and you'll see as you're looking at the actual execution mode whether or not you're running in row mode or batch mode. So if you have a cluster column store or a non-cluster column store index on a table and you're looking at the iterators to figure out what's going on, you see it's running in row mode instead of batch mode. I have some papers at the end of this talk that talk about some of the things that you can do to improve what you're seeing there. So global batch aggregation, a little bit more about that. At the end of the day, what it basically does is it processes the same amount of data with less memory, improves performance as you're doing the batch aggregations, especially with big hash tables is really kind of important there. It's just, for this group of people, it's probably just good to know that if you can get batch aggregation with your column store indexes, it's going to improve your performance significantly. Another thing that we do have is archival compression. So I've already talked a little bit about non-cluster column store indexes and how the final step it does is it compresses the data before it stores it into the column store index. You can, for any particular table, add an additional level of compression on top of that, or when I say table, I should say partition, that significantly can increase the compression by up to another 27%. So applying that per partition, so it can give you some additional archiving compression. Of course, if you need to query that data, it's going to be a little bit more expensive to bring it back off disk and process it through CPU. But what it can give you is the ability to possibly store more data in SQL Server than you might have otherwise done. So you might have been looking at storing, I don't know, 5 years of data within your data warehouse, and you're just really running out of storage space or what have you, and this might be an opportunity for you to store 7 years of data, where maybe the last 3 years or the oldest 3 years that you have are archivally compressed. And since you can do this by partition, you could partition at the partition level, archive compress that older data that is not accessed quite as often, so that you can store more data on disk. This is probably not something I would want to apply to the data that I'm querying most often. So in a typical data warehouse, maybe the last 18 months I'm querying 95% of the time. That last 18 months is something I probably would not want to apply archival compression to. But certainly some of that older data that we want in our data warehouse, we don't want to have to archive it out where we don't have access to it, but we don't use very often, would be a really good candidate for this. All right. So loading cluster column stores, what can we do there for efficiency? So this is getting into some things that you guys might be interested in. The motivation is for manageability over performance. So the idea is that we want to make it very simple to manage column stores. So when you're doing partitioning, a lot of times when you think of partitioning in SQL Server, you think of partitioning where you put different partitions on different sets of disk so that you can really improve performance of data, so you can get lots of parallel I/O going. And that's all fine. Really, for partitioning column store data, because we're storing it differently on disk, we want to think of it slightly differently in that we are not partitioning for performance, but we're partitioning for manageability of our fact table. I've worked with PDW for about 4 or 5 years now since it first came out. And PDW is our parallel data warehouse product, which means that we're dealing usually with large fact tables within PDW. One thing I learned moving deeply into the data warehouse space is that when you're dealing with a large fact table, like hundreds of gigabytes or terabytes of data, partitions are your friend when it comes to just managing everything that's in that table. Partitions are your friend when it comes to adding data to it. They're your friend to archiving old data. They're your friend when you need to rebuild indexes. They're your friend when you want to delete data and not have to delete it across the entire set of the table, and instead of focusing on partitions at a time by swapping them out and swapping them back in. Partitioning is really important in data warehouses. I cannot stress it enough. I pretty much tell customers now that when it comes to a fact table, every fact table should be partitioned. I know that whenever you say a blanket statement like that, there's always the exceptions, and I get that. But I start with the assumption that I'm partitioning first, and then I make the justification not to partition, not the other way around anymore. So that way we can do some very efficient things when we're bringing data into our column stores. mostly around building a table, applying our cluster column store, and then switching that partition into an existing table so that we can be very efficient about building indexes as necessary. Inserting and updating data. So like I said before, when you bulk insert data, it creates row groups of about 1 million rows. So if you're bulk inserting 10 million rows, we're going to create about 10 different row groups and put that into the cluster column store index. If, on the other hand, I have 10,200,000 rows, I'm going to create 11 row groups. The first 10 are probably going to be completely full. The last one might only have a couple 100,000 rows, but it is going to go ahead and get compressed and pushed into the clustered in column store index. It's important to note that if I now have a segment of I/O, because I'm reading by row group now, right, in segments, I'm now have when I'm reading that data I/O in, I only have 1/5 the data I normally would, which is going to decrease my performance. So you really want to have full row groups as much as possible. If your row groups tend to be very skinny, in other words, they only have a couple 100,000 rows or less in them, then you're not going to get the performance impact that you would if you had very full row groups. So those are cases where you might want to go ahead and rebuild those indexes to get fuller row groups. On the other hand, if I try to upload, let's say, 10,050,000 rows, I'll have 10 full row groups, and those 50,000 rows will be left in the row store, approximately. And then those 50,000 rows, as they get added to with additional inserts or what have you, will eventually get compressed and put into the cluster column store index. The insert update, all those inserts and updates get collected in the row store until we have about 1 million rows, and then it's converted to a column store row group. And that happens with what we call a tuple mover, which runs about every 5 minutes, which goes and looks at the row store and sees how many rows are in it, and if there's enough rows, it'll go ahead and do the processing of basically building the cluster column store index for that set of rows and moving that row group into the cluster column store index. And then you'll just have you'll now have your row store sitting there empty, waiting for the next set of inserts and updates to get collected. Or you could explicitly start it by doing the alter index on the table and doing a reorganizing and give it time. Batch sizes. So the tuple mover is the threshold for the tuple mover is about 100,000 rows. If it's less than that, it doesn't get compressed. If it's more than that, it gets pushed up. The idea that if you have batches of 90,000 row inserts, you're going to get large segments and be happy because they're all going to go into the row group. If you get 120,000 batch row inserts, they are going to actually be compressed and put into the cluster column store index. So the idea there is that you really want to kind of manage your inserts if necessary. You can get around a lot of this by inserting into a partition that is a separate table before, and then create your cluster column store index before you swap it into your final fact table. So if you can manage your loads so that you are creating a staging table that essentially looks exactly like your fact table, insert all the data into it, create your cluster column store index and compress everything, and then switch it in as the last partition, then you can avoid a lot of these headaches, especially if you're not updating or deleting any data, and then you just have as full as possible row groups sitting there for each partition, and that's a really good way to handle it. So building cluster column stores or column store indexing is very memory resource intensive. As you can imagine, all those rows have to be in memory, then we break them out into segments, and then we compress them. That unit of parallelism is the segment, so the more segments you have, that is the more columns you have, then you have lots of potential parallelism. And then finally, low memory will throttle parallelism, and this is kind of important to know from a couple different aspects. If you have memory problems on your machine, you have lots of other things going on when you're compressing your column store indexes. If SQL Server runs out of memory for you, it will essentially start compressing those column stores and creating smaller row groups. So if you find yourself looking at your cluster column store index and you're seeing lots of row groups, maybe in the thousands or tens of thousands even, then what's happening is that during the creation of your column store indexes, you're just plain running out of memory. And because of that, SQL Server just doesn't have any memory to do what it needs to do, so it takes all the segments it's already compressed and it just writes them to disk and then takes the next step. You can avoid this by having more memory available to your system when you are compressing your data. And you can do that by increasing your max server memory option. You can add physical memory to the system. You can, there's lots of things you can do to kind of play around with it. Adjust your DOP and segment size possibly are some examples. And if you give presentations, you should always turn off your notifications. The idea there is that if you do those things, you should be able to avoid that. If you're just compressing a small daily data that you're bringing in, this probably wouldn't be as much of a problem as it is if you're trying to do your initial compression of a large table. If you have several large tables you're trying to do this with on a busy table or a busy server, you may run into some of these problems, and you'll see the effects of it as you're looking at your sizes of your row groups later on by looking at the DMVs that are available to do that. So these are some things you can do. So optimizing database and index design around cluster column stores. So let's ask the question, non-cluster column store indexes, do we still need them? Yes. If you need constraints or triggers on the table, creating a cluster column store index will fail if there's a B-tree index enforcing a key constraint. So one of the things that you will notice about cluster column store indexes is that you can't have any other indexes or other constraints on your table. And for some people, that is a non-starter. For others, you think it's a non-starter, but if you really start talking about why you have those things there, you realize that some of the things you're doing with indexes or other key constraints you can do through the ETL process, for example, or just plain deal with them at a higher abstract level. For example, if you need a B-tree enforcing a key constraint, you could then create a table with clustered index and then add non-cluster column store indexes would be one way to get around that. So add non-cluster column store indexes to all the rest of the columns that you want to get this kind of performance on. However, you wouldn't be able to update the table if you do that. On the other hand, if you have no constraints needed and you are dealing with typically a fact table or a large dimension table that you don't update very often, non-cluster column store indexes could eliminate the need for all your other indexes. And you could just create the table and have the cluster column index, clap your hands, shake them, and say, I'm done, and not have to worry about that because no other indexes are needed. You can do all your inserts, updates, and deletes as needed and just manage your table that way with consistent fast query performance. If you need to update a non-clustered column store, that is the non-cluster column store from SQL 2012, that's still available in 2014. Some recommendations are you can disable your index, update the data, and then rebuild, or you can use partition switching to switch things out, disable the index, update it, and then switch it back, add it back in, and then switch it back in. Or you can use a delta table and union off. So what is that? What am I talking about there? Think of the vision of the cluster column store index, how we have this cluster column store table, and then we have this delta store, right? Well, you could virtually do the same thing yourself with two separate tables and a view over the top of the union between the two tables. And as you do inserts, you could insert that data into the heap, and then once a day or once a week you could process that into a partition and switch that in, or just drop the index from the original table, the original fact table, add the data in, and then re-add the index, and then you would have an empty kind of delta store for the next week. You could deal with updating a non-cluster column store. So if you have these constraints up here where you still need a non-cluster column store index because you have some sort of B-tree constraint, you could create your own delta store solution with a union all view over the top. That might work okay for you so that you can kind of get a best of both worlds. Other considerations, though, there are considerations such as no other indexes are needed with cluster column store. In fact, you cannot make them. They're just not available for you to do. What this does is, though, it saves us a lot of space. It saves us a lot of maintenance work now because now you are not spending hours upon hours every week trying to update the dozens of indexes that you might have on that table. There's no real need for other indexes with non-cluster column store either, except for maybe your clustered indexes. And then really the partitioning works for both cluster column store and non-cluster column store. And like I said before, it's really good for managing the lifecycle of data. creating the data in a separate table, switching it in. If you need to archive table, switch out your oldest partition into somewhere else, and then archive it off. It's especially great for non-closure column stores where deletes aren't possible, but I really recommend it for any large fact table that you might have. If you have strings in your table that you want to use for column stores, you can design those out of your table. So if you have some sort of string like this, you can do something where you factor them out of the dimensions, where you take like a dimensional table that might have some strings in it and break that out into two separate tables. They're joined together now. So now I can do my clustered column store over the table that has date and license ID and measure. And then I can do a non-clustered, I can do just a typical clustered index and non-clustered indexes over the other table with license ID and license number. And then I could put a view over the top of that, and that would work well for my end users and still give me some of the benefits of the cluster column store data that's sitting in my dimension, or maybe even a fact table. So it's a way to kind of design out some strings so that you can still use your column store indexes. Considerations for moving the column stores. So you have an existing data warehouse you might want to move. Some things you might need to do for existing tables. You'll need to drop indexes and constraints, create your cluster column store index, and then allow people back in. Obviously, this is going to be best done when users are querying, especially if this is a really large table. This might take a while to do because it is fairly CPU and memory intensive. The less users you have on the system, the less likely you'll run into the memory constraints that I talked about, which means it's more likely that you'll have nice full row groups as you get done. On the other hand, if we're talking about non-maintenance windows, and because you have a 24/7 operation, there is a path to do that by creating a view over your fact table. You redirect to your existing table, create a new table as a cluster column store index, copy all the data to the new table. When the new table is finally up to date with all your recent additions, you can then change the view, and that should work fairly well too if you need to do that. Moving on to some query optimization. The idea really for the best place to use this is really in a typical star schema where you have column stores on fact tables, and we have lots of integer circuit keys out to the joins of the dimension tables, and this really improves the performance of those joins to the dimension tables. And then when you do this and you just do the star schema and you have the cluster column stores on your fact tables, it really allows you to not have to worry about indexes on the rest of the columns, figuring out whether or not you need compound indexes or any of that kind of stuff. You can really just worry about writing the correct queries and moving on and not have to worry about a lot of the lower level stuff because the efficiency just takes care of itself. Because really at the logical level, there's no real difference between cluster column stores and regular tables. So in summary, think of the three canaries in the coal mine when you explain why cluster column stores are important. Some disk I/O, memory, and CPU. Or disk I/O, CPU, and memory, right? So cluster column stores reduce the amount of space you have on disk for a particular fact table, which means that you have a lot less I/O that you have to push through the system into your CPU to store in memory. And when it's sitting in memory, it takes up a lot less space because it is very highly compressed, and we can eliminate a lot of the columns that we may not be querying on a regular basis. And so it really improves the performance of the three canaries in the coal mine through the cluster column stores and the space saving and the batch mode processing also to really improve performance of your fact tables. Anecdotally, what I've seen out there live in the world is that when you apply cluster column stores to fact tables on existing systems, what it really can do is it can breathe new life into an existing system. So a data warehouse where you're thinking you're going to have to go out and buy a new server because you're just running out of CPU time and storage space for a particular data warehouse, this is a place where now all of a sudden that same server and that same storage has a few more years left of life in them that you didn't have before. Is definitely one scenario. And it can also be another scenario where you're looking at data warehouses that you might not have considered for SQL Server because you might have thought that they were too large and SQL Server might not have been able to handle them. Makes them prime candidates for SQL Server because the cluster column store really takes us up into the dozens of terabytes range that we can easily handle without real significant design issues. It really should improve the performance that you're seeing. Within the deck that I'll share out to Rob, and I'm sure he'll share out to you guys, there's some links to some additional reading material out there for anybody that's interested in all that stuff. I'm really, really sorry that the demo didn't work. I don't know what happened there. It looks like something got hung up, and I knew I barely had enough time to get through the talking as it was. So I wanted to make sure we covered the material. If there's enough of a request out there, I can go ahead and record the demo and give it to Rob, and he can post it up on YouTube for later perusal if you guys are interested. Just let them know. Anyway, I got a couple minutes for questions, or if Rob, if you have any questions you want to push out.
Well, we have one question here. I'm going to go ahead and bring it up since we have a few minutes.
Okay.
Basically the question is, will Columnstore Index provide improved performance on, say, a replicated reporting database based on an OLAP database design?
All right. So will it provide improvement for replicated reporting database based on an OLAP design? Maybe.
Yeah, that's kind of neat.
Answer, it depends. I don't know how big that database is. I don't know what the replicated part, why that is important to know.
Yeah.
I honestly don't know if you can replicate a Columnstore table, to be honest.
Yeah.
I would have to look that up, because replication generally requires a primary key. And so it may be, and I'd have to go look it up, but it may be that a Columnstore table cannot be replicated, which would make that I would say no, that probably wouldn't be a good candidate, would be my guess. But I'm just guessing there based off knowledge of essentially two different things.
Well, Brian, thank you for spending an hour with us at our virtual chapter today. I mean, it was great. I'm lost of words. It just felt great. And if anyone else has questions, email me, and I will make sure Brian gets, Brian gets the questions. And it was really a great pleasure having you today. Thank you for doing this, Brian.
Thank you. I appreciate it.
And I'm going to stop the recording. We're going to post it on YouTube, and I hope everybody has a great Friday and a great weekend. Thank you again, Brian. Talk to you later. Bye.